I'm Sorin Paraoanu. I'm from Aalto University in Finland, and I'm going to talk about a few experiments and also the theoretical things that we worked related to superconducting resonators that have some nonlinearity and that are driven parametrically. So let me start by saying that our aim is twofold. One is to understand the physics of critical parametric sensing, and the other one is to really develop some useful device that could be used for detection of microwave photons for nanoelectronics, device that would have quite a number of applications. As you may see here, some references of people doing their best trying to realize this type of devices. And you can see that some setups are quite complicated. They are also could be very good, but the level of involvement into building these devices can be quite demanding. And therefore, we are thinking of what about something simpler. And we think that what we are doing is actually addressing exactly this type of problem. So let me start by a practical problem, since I come from Finland where things get all the time frozen outside. You see that if you have a bottle of whatever water and you want to use it as a way to measure the temperature, then well, it's not so easy to use it if you are at room temperature or at some kind of above zero temperature. Uh, it will The level here will change a bit. Of course, the water would dilate a bit if the temperature increases, but not enough to be able to use it as a real thermometer. But something happens around the freezing point of water, namely that you can see visually that the water got frozen. So if you are in a certain range and if you are using a phase transition, you can have a very, very sensitive sensing device, a thermometer in this case. So the idea generally is to try to use this kind of phenomenon, phase transitions or critical phenomena. How about using them to do some sensing? And you have seen in Roberto's talk already this slide where uh, there are theoretical estimations of what we would gain if we would use parametric sensing. And this is the typical Kerr Hamiltonian. You have some frequency here of a harmonic oscillator. You have a pump here and some kernel linearity. And what it was shown in this paper is that indeed there is an optimal way of setting these parameters epsilon such that the signal to noise ratio is quite high here. And also if you calculate the Fisher information, it also reaches quite good, very high values. And this thing happens near the phase transitions. So near the phase transition. So this is a theoretical, very general theoretical calculation. Now the question is what happens. So we are an experimental group, so we are thinking what about experiments. So how to realize this parametric oscillator? It's quite simple actually. You have devices called typically just some parametric oscillator. They are like a resonator terminated with a squid. You can bias the squid here and change the effective electrical length in this resonator. And then here is a kind of a more sophisticated biasing scheme to avoid some overheating of the device, but essentially it puts a magnetic flux through this squid. And then you measure what comes in, you put something in, you measure what comes out. And typically these devices are used as amplifiers, quite narrow band amplifiers, but they work quite nicely. All right, so can we write something that looks familiar to quantum optics um, practitioners? In fact, yes. So this is the standard Hamiltonian that we would write also for this device. It looks like something that we have seen many times. It has a kernel linearity, this fourth order here, and then it's parametrically pumped with some pump frequency omega p. It has some frequency as well. And then next thing that we want to do is to solve this system. And that's what I will spend the next quite many slides on. It's going to be a bit theoretical and technical, but the point that I want to make is that there is a method by which this terrible device, in the sense that it has so much nonlinearity and looks so complicated, can actually be solved and understood in a very intuitive way. So, as I said, we start with this Hamiltonian, and then we do the usual thing, which is a transformation in a rotating frame rotating at half the pump frequency. So you write down then the Heisenberg equations of motion for this system. In this way, it just comes out from the Hamiltonian. We do the usual rotating wave approximation and so on. And then what we will want to do is to go to these quadratures, which are P and Q here. These are the field quadratures, or like momentum and position in quantum mechanics. And we want to write the system in the system Hamiltonian in the rotating wave approximation in terms of these quadratures. And it looks like this. So PQ terms here, P square Q terms here, this kind of term here. If I write down the Heisenberg equations of motion now, it looks like I have done some going on some terribly complicated path. And because I get extremely complicated terms with cubic terms here and so on, it looks like I'm not getting anywhere. But in fact, I am getting somewhere, because then the next step, important step, is to notice that these P quadratures, if you are close to a phase transition, which we will later clarify a bit more, but if it happens that this term is a bit larger than this term here, then this P guy, this P quadrature, oscillates very fast. Therefore, I can do the following approximation. I can consider it as a fast variable, and I can take its derivative to 0. And then what I'm going to do is to go back to this system of equation. I extract P from here and I plug it in the equation for Q, and I get something very, very nice. I get um, an equation that describes the motion of this Q quadrature in a potential that has essentially this term. This thing is a constant, or I can factor it out, and the essential information is in this effective potential that I'm going to discuss quite in detail. What happens here is that we have a quadratic term, a quartic term, and a sextic term, which is very interesting, because if you remember the theory of phase transitions from Landau, that's exactly the standard type of free energy functional that it's considered there. And so if we plot this potential, this effective potential, as a function of the parameters alpha and delta, let's remind us that alpha is the effective pump, is the strength of the pump, and this delta is the detuning with respect to half of the pump frequency. And it's convenient also to normalize these numbers by the dissipation and couplings to the output world, to the outside world that we have in the system. We will get this phase diagram. And all these points in this phase diagram that are plotted here, you see that they correspond to different type of features that we see in this effective potential. So for instance, nothing much happens in this blue region because it looks like a parabola here. But already in this yellow region, like if I look at point 3, you see the appearance of two dips here. And the interesting feature for us is what happens in this at points 5 and 4. 4 will be what we call the operational point of our device, where you see this little dip here developing, this metastable state developing. So what we will do briefly is that we want to trap our sort of particle here, this particle described by a coordinate or momentum q. We want to trap it here and then let it go over this hill here to either towards the left or the right wells. So this is what is going to happen, in fact, in the experiment. First of all, we can write, based on those equations, we can write Fokker-Planck equations based on the Heisenberg-Langevin equations that looks like this, with a dissipation term and with this potential U that I just mentioned. But essentially, if we don't do anything to this potential, that our particle, it means that it will stay here. And if I take a closer look at the particle here, after some time it will diffuse into these wells that are a bit farther away. This phenomenon is responsible for the dark counts in our system. And we can solve this Fokker-Planck equation numerically, just integrate it and then put some kind of thresholds to decide whether the particle has switched or not to these outer wells. And it looks like this. So we start with the probability. This W is probability distribution. We start with it as being somehow centered around the zero position in the middle of the well. And then you see that as time goes by, it tends to diffuse into equally into the left and the right wells. These are the larger external wells at larger positions, larger Qs. Now, what happens when you do something to the system, namely what we want to do is to put an external field, a very small external field, in our case, that has a few or zero microwave photons in it. What happens is that one can show that the physics changes in the sense that this potential acquires a term which is linear in Q, which effectively means that we have tilted this whole structure. So this particle that was diffusing with equal probability before in the wells, now it has a higher probability of going into the well towards which it's tilted. Yeah. So we start here, and then it will slowly, or more faster than before, move in this well. And this is our click. This is when we know that probably we have had a photon in the system. We can do the simulation, of course, also for this case. So we start with this probability distribution. Again, it diffuses, but now you can see the tendency already here is predominantly towards the left. So it goes with higher probability in this well rather than in this well. You can see the difference in scale here. This is 0.2, this is much smaller. So it goes, things go in the kind of correct direction from the point of view of our intuition. Now I'm going to have to introduce a few notations that are maybe not so easy to digest immediately as you see them, but essentially what we want to say is that there is a probability P1 plus, small p1 plus, which is 1 minus exponent of minus eta n bar. And this eta is defined for the theory of threshold detectors. This is going to be a threshold detector as being the efficiency. And this is valid for coherent states. And then we define as P1, large P1 plus, as being the probability that we actually measure under when we have some probe field at the input. And this contains also these dark counts. And then the probability P0 is the conjugate of this P1 plus. So they sum up to 1. So then one thing that we need to do is to try to understand actually what is going on in this system from a theoretical point of view. And the first thing that we should check is whether our approximation that we performed actually makes sense from the physical and numerical point of view. So we took this kind of equation and we did numerical simulations here. And what you see here is that indeed this probability P tends to be much smaller or generally smaller than the probability Q, which is a consequence of our approximation that we just did. It turns out that that's the case. So things are consistent and working very nicely. And then another question that we could ask is whether can we really solve these equations analytically? And surprisingly, the answer is yes, but only in the case when the system has a zero Kerr constant. And in this case, they look like this. So this equation for Q looks has this form with a constant B here and with a factor S here, which depends on how close you are to the phase transition, to the boundary of the phase transition. And this is a kind of generalized Ornstein-Uhlenberg process. And we found out that it has a solution that can be written in a very simple form. Actually, this very, it's Gaussian form where this average and the variance can be calculated exactly. So this is quite nice. We have even analytical solutions for the situation where the kernel nonlinearity is zero. And then you can go farther. If you really are very close to the phase transition, then you recover the Fick law in which these averages are and this variance is proportional with the time. Yeah, so we can do the simulations and we can find out things that happens at around the phase transition. For instance, we can calculate this efficiency that that I discussed before. And in the end, what we want to do is to compare all these results of the simulations. So what we plot here is the numerical results of the Fokker-Planck equation and of the Heisenberg-Langevin equation. The Fokker-Planck equation is approximation of an approximation already of this Langevin equation. But what we find out here is that they give quite reasonably close results to each other numerically. So everything seems to be quite consistent. And so we can also think about efficiency, and we can it could be extracted from these probabilities that are plotted here. And so everything from the theoretical point seems to be quite consistent. And now I'm going to spend just a few minutes talking about the experiments, because fortunately there's not much to say except that the experiment works very nice and the results are in very good agreement with what I have just said. So that's my message. What we have is this machinery here, which is quite complicated for people who are into it. I can explain what they are. But essentially it's superconducting circuit here, which is the same as what I showed before. It's a resonator with a squid at the end that realizes exactly this device that I told you, with kernel linearity of the order of below kilohertz, and all the other parameters can be extracted from the experimental data. And what we see is the following thing. This is the phase diagram observed experimentally, which is quite nice, and it's exactly what we were expecting to see. We can look at all these points and measure the fluctuations. So these are real experimental results. Even they look very smooth and very nice, but they are measured over quite a lot of time, so that we can see them very nicely. And they all behave as they should. So we see vacuum, squeezed vacuum, oscillatory states. Everything seems to be exactly in agreement with the theory. And the way in which we are setting up our experiment is that we have a probe off case and a probe on case. We put pulses here, corresponding to bringing the system to the operational point, pulses in the pump. And then during these intervals when the pump is on, we can measure the coherent field, which is at the input of the device in the probe on case. And then this guy switches to this state or doesn't. and then we can calculate probabilities. It's actually quite involved because this is a threshold device. These are experimental data, by the way, how they look, how it switches. But we have to decide at some point whether the detector has switched or not, and this is the result of a quite involved analysis looking at the signal and what happens when it switches. Maybe this is a bit more clear if you have ever seen how people do things in radars. This is a receiver operating characteristics in which the dark count rate is plotted against this P1 plus rate. And it looks like this. It curves in the upper part, which is how it should be. And this allows us to identify the optimal way of measuring the device, namely the optimal threshold that we should put here to get the best results based on maximizing this product of probabilities. But essentially the experimental results are here, fitted with a number of theoretical approximations and numerical results. And you see that the fit is actually pretty precise and quite good. So these are the raw results here for P1 plus, and this is what we extract for an ideal detector in the absence of the dark counts. All right, what we can do, a few other things are to look at the Poissonian distribution, to try to extract something about the distribution of the field. And we can actually, even if it's a threshold detector, we can show that we can extract some information about the Poissonian distribution of the coherent field, which is in front of the detector. Okay, there is more to it. We can go deeper to look at this Poissonian distribution by separating the counts into bins and by using a binomial distribution with the input in each bin corresponding to the probabilities that we are measuring that we have seen before. Okay, to conclude here, what we worked on is a parametric phase transition. From a theoretical point of view, this is a great machinery because it's a paradigmatic system that has a lot of connection with this Lipkin-Meshkov-Glick model, with the DCAM model, with PT symmetry breaking, and a few other very important models in many body physics and optics. And from the standpoint of practical applications, detecting microwave fields at very low number of photons is a very important application. And let me advertise in the end one conference that we are organizing on detectors in August in Helsinki. You are very much welcome if you still have energy for this summer to come and participate. Thank you.
Thank you, Sorin. Are there questions? So maybe I start over there.
I do not know much about it, but there at the last slide, you can say, like you said, the conclusion. So you basically set the experimental setup to have like Kerr linearity and other stuff, and then you can solve or model. Sorry. So, can you like briefly explain like how do you like access the critical point experimentally?
Yeah. So what we have here is the phase diagram, which is observed experimentally. So what we can measure are the quadratures of the field at any moment of time. We can measure them, and if you calculate then the fluctuations or averages or any kind of quantity, they will look like this. There is going to be a phase boundary like this here. So these are external parameters that we put here. We can increase the pump and we can change the detuning. And we see this quite nice feature, which is exactly the theoretical prediction. And what happens is that this is a phase or first order phase transition at this border, and this is a second order phase transition. And in this tip here, the bottom is a three critical point. This can all be calculated theoretically, analytically, very nice, actually. And so we can put ourselves in, I mean, we can set the system in whatever point we would like to be. And for us, the best thing is to be somewhere close to this first order phase transition, because that's where the switch is quite sharp from one position to another. We can clearly see it. And it's also fast. So whenever a photon comes, we are here, a photon at the cusp of the transition, we are here. You can imagine it's like a sudden change, tipping the system into another phase, essentially.
Can you cross the border adiabatically, or
We can, yeah. We can change these parameters and we can access and explore any point that we want. In fact, that's what we did here. So these are just some random points that where we collected data to show that what is the stable state, what is the stationary state in each of these points.
Thank you very much.
Very interesting talk. Could you please tell us how quickly the system recovers, or at what bandwidth you can measure?
Sorry, can you repeat about?
At what frequencies can you detect photons,
Yeah,
and at
yeah.
which bandwidth, how quickly does the system recover for the next photon?
Yes, good. So the bandwidth is, so we measure around 6 gigahertz. The bandwidth is limited by the this K parameter, small k parameter, which is the decay rate of the resonator, and it's emitted to a few megahertz. So it's bandwidth limited in this sense. And what we are doing here, that's why this system is paused, is because we want to leave the system a time to recover, which is again of the same order as this pulse is around 1 microsecond. So if something gets detected, then it switches to these external wells. Then we have to retrap the system to be able to start another detection, for the next time. And so for this, we wait something around 1 microsecond. So this is like if we can miniaturize the device itself, it's already small. I mean, it's this. It's of course the limit is limited by the length of the resonator. It has to be, which is limited by the 6 gigahertz wavelength of the microwave.
Are there more questions? If not, then let's thank Sorin again.